Assalamu alaikum, everyone. So in the last class, we are done with uh, till question number 2. We were doing February, March 9701, paper 4-2. And now we are going to start with question number 3. Okay. So Fe2 positive and Fe3 positive ions are able to form variety of complexes with different species. Define a complex. So a complex is a molecule or ion in which a transition metal ion is bonded to ligands by dative bonds. You can further add that electron pair is shared. Electron pair is shared from ligands. And if you don't add this point that it is not necessary, the definition till here, that it can be a molecule or it can be an ion in which a transition metal ion is bonded to a ligand by the dative bond. Okay. Now they are asking for table 2.3, right? Table 3.1 gives some details of different complexes of Fe2 positive and Fe3 positive. Complete table 3.1. So, okay. In the first one, you have a transition metal ion, Fe2 positive. The ligand is ammonia. Coordination number is 6. So it's a monodentate ligand. So it means each ligand can form only one dative bond. So it means iron is going to bond with 6 ammonia molecules and ammonia has no charge. So the net charge of the whole complex is going to be 2 positive. Okay. Now in this case, there are 4 chlorides. In the second case, there are 4 chloride and chlorine is also a monodentate ligand. So the coordination number is going to be 4 and Cl negative is a ligand. And if you see the net charge is 2 minus, chlorine is 1 minus, and there are 4 of chlorine. So it means the iron must be +2. So over here it is Fe2 positive. Okay. Now, next part, En. If you recall, En is a bidentate ligand. So, and there are 3 of them. Bidentate means each ligand ion or molecule is forming 2 dative bonds. So there are 3. So 3, each one is going to form 2. So 3 are going to form 6. And En, as you see, there is no charge. So the 3 positive is the charge of the transition metal ion. So over here it is Fe3 positive. I hope it's clear to all of you. Okay. Now next. Complete the diagram 3.1 to show the splitting of d orbital in tetrahedral complex. So remember, the tetrahedral complex is the one in which there is the splitting would be like this. And if the complex is octahedral or square planar, the complex is octahedral or square planar, then the 2 set of orbitals goes to the higher energy and 3 set of orbitals goes to the lower energy. So it is going to be 5 orbitals over here, 1, 2, 3, 4, 5, with the same energies. Then from here you will split into 2 sets. So the 3 set of orbital is going to be at a higher energy, and 2 set of orbital is going to be a lower energy. If you want to label them, so it is dxy, dyz, dxz. And over here, one is dz square and the other one is dx square dash y square. No, don't write it in the boxes. Either write it below the boxes or above the boxes. Okay. Now, table 3.2 gives the details of some complexes of Fe3 positive ion. Okay. Explain the reason for the difference in color of the two complexes of FeH2O63 positive and FeH2O SCN. So they are asking for the uh, difference in color, and it's for 2 marks. So the simple reason over here is uh, that the ligands are of different strength, right? No, don't mention stronger ligand. It's better that there are different ligands, right? So there are different ligands, right? So as we know that different ligands have different strengths, due to which the energy gap, or you can say the splitting, the energy gap between d orbitals differ. Hence, the hence different complexes absorb light of different wavelengths. So if they absorb different wavelength light, they are going to emit different wavelengths. So as a result, the color gets different. Absorbs the light of different wavelength. Okay. Yes, yes, Fazil, it can be written. Let us write as well. Okay. Now, part 2, write an expression for a case step for FeH2O SCN2 positive. So remember, whenever they ask you to write the case step for any complex, so it is when that complex is actually uh, formed from its exact work complex. So it means if they are asking to write the case step for the complex which they have mentioned, so it's basically 3 positive, right? And it is reacted with SCN negative, forming FeH2O5 SCN 2 positive, and then uh, 1 H2O is released. So remember, whenever we write the K-step expression, uh, we are not going to write this H2O, but the rest of the things. And it's a equilibrium constant. So in the denominator, in the numerator, we are going to write the complex which is formed at the product. And in the numerator, it is 5H2O, 3 positive. Okay, put it in another square bracket because the first square bracket is of a complex, so the second square bracket is of a concentration. For SCN, you can put just concentration. Okay. Now, use information in table 3.2 to calculate the value of the equilibrium constant Kc for the following reaction. Okay. Now you need to calculate the value which, okay. So if you see, you are provided with the K step for water. You are provided with the K step for SCN2 positive, and you are provided with the K step for F. Okay, so if you see, these two are actually also, if it's a K step of these two, so it means these two are also formed from the hexaaqua complex of iron 3 positive, right? Actually, these two are, this is also formed from this, and this is also formed from this. That's why we are getting these values. So you can make the Hess cycle for a Kc expression. Okay, that's fine. So for a Kc expression, you have to calculate the Kc value, right? So you are given with the values, and you are going to put these values over here. So the Kc is actually equals to, if you see, the Kc is equals to, if I write the Kc expression, so the Kc expression is going to be like this over. So see, your one complex, the fluoride complex in the denominator, and the thiocyanate complex is in the numerator. So what you are going to do, you are going to just take their uh, K step values from here and put it over here. And then on solving, you will get the answer. So it is going to be 2.40 exponent 5 over 1.40 exponent 2. So that is actually the shortcut way which I am telling you. Otherwise, if you have to derive using these, so it will take a lot of time. So remember, whenever examiner asks you to write the Kc expression for any equation, where the complexes are there and you are given with the k step values. So if the complex is in the numerator, put its k step value in the numerator. If the complex is in the denominator, put its k step value in the denominator, and don't ignore their concentration. That's it. That is the shortcut way of solving this. Case tab refers to with this when something is forming from the water complex, then it is case tab only. If the one complex is turning into another complex, but neither one of the complex is a water complex, then we can't say it's case tab. Case tab is for such a complex when the complex is formed from the water complex. That's it. Otherwise, it's not case tab. Okay, Faizan? Okay. So can anyone solve it and tell me the answer? Okay. Shahir, it's 1.71 exponent 3. Can anyone cross check it? I just want to sure that no one did any mistake. It's not exponent. Okay, exponent 1714.3. Okay. So if it's tried 1714.3. So the KC is 1714.3. Okay. Now next part. Part 4. A few drops of KF are added to a solution of hexa-aqua iron 3 positive complex, followed by a few drops of KSCN. With information in table 3.2, describe any observation after each addition, explain your answer. Okay, so for that, if you see, it's exponent 5, the complex having a fluoride, and the complex having a thiocyanide, it's exponent 2. So which indicates that this one is more stable. This one is moderate stable among the three. And this one is least stable, right? From the values, you can figure out by the values which one is more stable. So initially, see what they are saying. First, you are going to add KF, which is going to give you the fluoride ion first, and then SCN is provided at the second place, right? So And if you see SCN is a smaller, is less stable than the fluoride ion. So when we add fluoride ions, K or KF, this would react with this to give you this. Now the solution has this complex. Now if you add thiocyanide and or adding this, because its values is smaller, it would not do any reaction, so no reaction would occur in that case. So initially, the color changes from violet to colorless when you have added potassium fluoride, and then no change. Yes, very good, Shazil. So, uh, on adding KF fluoride displaces water. Okay, they ask you to describe any observation and then explanation. Okay. So on adding KF, it's violet to colorless. The color of solution changes from violet to colorless, and then adding KSCN will give no change, as the K step value for, just give me a minute please everyone. Okay, so the K step value for FeH2O5F is greater than K step of FeH2O5 SCN. Okay, yes, Arish, we can identify from their values. So see, you have this and you are adding fluoride, so you will get this complex. So this complex has a greater value. So the color changes from violet to colorless. But when you add SCN, so SCN has a smaller value than this one. So SCN would not able to, so this complex would not able to form. Is this clear? Okay. Now, C part. Hydrated compound JK3FeC2O4 thrice XH2 contain the green complex ion FeC2O4 thrice 3 negative. The value of X can be determined by titration a sample of J with acidified manganate ions. Manganate ions oxidizes C2O4 in an acidic condition. So here we have an equation and we have a ratio of manganate with the ethane dioate ions. Okay. Write the half equation for the oxidation of C2O4 ions for the reduction of MnO4. So if you see, C2O4 is turning into CO2 and MnO4 negative is turning into Mn2 positive. And they are asking you to write the ionic equation for both of these, right? Okay. So from here, C2O4 2 negative is turning into CO2. There are two, so I'm going to put 2 CO2. Is this clear? Now, if you work on the oxidation number of carbon, so it is minus 2 times 4, which makes it minus 8. So the carbon is plus 3 over here. So the carbon is plus 3 over here and the carbon is plus 4 over here. So it means the carbon is losing one electron. So there are two carbons, so they are going to lose two electrons. Is this clear? So we are done with the half equation of C2O4 because we have a carbon, two carbon on both sides, four oxygen on both sides, and the loss of electron is also justified. Yes, very good, Arish. Now, for MnO4 negative is turning into Mn positive, 2 positive. So Mn is plus 7 over here for plus 7 to plus 2, which means 5 electrons are being added. So I'm going to put 5 P negative over here. So there are 4 oxygens. Oxygens are always balanced by adding a water. So there are 4 oxygens. So I'm going to put 4 water over here. And 4 water makes 8 hydrogen. So I'm going to add plus 8 H positive over here as well. So now my half equation is done for the MnO4 negative as well. So that's how you can make the half equations. Okay. Now, 1 minute, please. Okay. A student prepares a solution containing 0.100 gram of J. A student titrates this solution with 0.02 mole per dm cube acidified potassium magnate. The titer is 12.2 centimeter cube. So this is the volume of KMnO4 and this is the concentration of KMnO4. Assume all C2O4 2 negative ions are oxidized. Calculate the value of X in. So, okay, over here we have to calculate the X. Okay, so if you see, this whole is a one compound and this one is going to give you 3 moles of C2O4 2 negative. Isn't it? Is this point is understandable to all of you? Okay. So first what you are going to do, you are going to calculate the moles of magnate. Okay. So, and you have the MR of this whole compound. Okay. So moles of KMnO4, you are provided with its concentration and volume. So concentration is 0.0200 multiplied by volume is 12.20, which is in centimeter cube. So you divide it with 1000 to turn into dm cube. So can anyone tell me the answer, please? Okay. It is 2.44 exponent minus 3. So these are the moles of KMnO4, right? So if you see over here, the reaction is between KMnO4 and C2O4 and the ratio is 2 is to 4, 5. So first we calculated the moles of KMnO4. In the second part, we are going to take the ratio of a KMnO4, potassium magnate with C2O4 2 negative. The ratio is 2 is to 5. So if we have 2.44 exponent minus 3 moles of, then how many moles of C2O4 would be? So we will calculate the moles of C2O4, which is equals to 2.44 exponent minus 3 times 5 over 2. Can anyone tell me the answer, please? Okay, it's exponent minus 4. Sorry, my bad. My exponent minus 4, exponent minus 4. Thank you, Fazan. Exponent minus 4. Yep. Just give me 1 minute. So yeah, on dividing with 2 and multiplying by 5, okay, we will get 6.1 exponent minus 4. So these are the moles of C2O42 negative, right? Now, we have identified that 1 mole of a complex has 3 moles of C2O4. So with C2O42 negative is to complex, the ratio is 3:1. So if we have 6.1 exponent minus 4 moles of this, then how many moles of complex would be? The moles of complex would be X. So X is equals to 6.1 exponent minus 3 divided by 3. Yes, Amna, we did the ratio from here. See the equation. Okay. So it is going to be 2.03 exponent minus 4, right? So these are the moles of K3FeC2O4 thrice. Okay. And these moles are present in 0.1 grams, right? Okay. So now we need to calculate the value of X. We got the moles. We can calculate the mass, that how much mass is present of just this one without water. So what we are going to do, we are going to multiply the moles with the MR, which is 437.1. Can anyone tell me the value? You can do this way, or you can do another way, that these are the moles and this is the mass. So it will give you the mass of the hydrated one with the XH2O. So mass of, it is the mass of, from this you will get the mass of anhydrous. Or you can go for the mass of hydrated, you can get the MR of hydrated one. MR of hydrated one with the water of crystallization. So the MR would be mole is equals to mass upon MR. So MR is equals to mass upon mole. So mass is 0.100 over 2.03 exponent minus 4. So MR of hydrated is 491.8. So from this is the MR of anhydrous, this is the mass of hydrated, so we can calculate the mass of water. So the mass of water is going to be 491.8 minus 437.1. Can anyone tell me? This way you can do this, but it is a longer method. So better to go for the MR and then subtract it. Okay. So 54.7, that is the mass of water. And if you divide it with 3, it will give you around, oh sorry, you can divide it with the MR of water. So that will give you the value of 3. Thank you, Fazan and Arish. So the value of X is going to be 3. Is this clear? Okay. Now, question number 4. State the difference in the basicities of ammonia, propanamide, and propylamide. So if you recall, amide are relatively considered as neutral. It's a weak base, as ammonia has no electron donating group, and it is a relatively a stronger base. So among these, it is going to be the strongest one. So the strongest base is propylamide, CH3, CH2, CH2, NH2. Remember, alkyl amines are the stronger one than ammonia, and amides are weaker. And over here, CH3, CH2, CONH2. So, yes, very good, Arish. So, first point, it's better to write that the uh, basicity, or you can write that the basic strength depends upon how readily the lone pair is available to accept a proton, a hydrogen ion. Yes, Faizan and Arish, very good. So we can start with propylamine. And if I use its shorthand form, it is going to be C3H7NH2 is most basic due to alkyl groups electron donating nature. Just give me 1 minute, please, everyone. Okay. Due to the alkyl group's electron donating nature, the lone pair on nitrogen is readily available. Then you can go for ammonia. Ammonia is more basic than C2H5CONH2 as in ammonia, nitrogen is not bonded to any electron withdrawing group. Hence, its lone pair is more readily available to accept proton. And then propanamide is weakest as lone pair. Yes, very good, Shazil. Lone pair on nitrogen is delocalized due to C double bond O, hence not available to accept hydrogen ion or a proton. Okay, now figure 4.1 shows two different ways to synthesize propylamide. Okay, in the first case, reacting with ammonia and giving you an amide, and that amide is turning into propylamide. Over here, an alkyl halide is reacting with KCN to give you a compound L, and that is again turning into M. Yes, Shazil, very good. So in the first case, the K would be, if you see, it is going to be CH3, CH2, COCl. So Cl, the NH2 is replaces the Cl forming amide. Okay. Over here, if you see, you are using KCN, so the compound L is going to be CH3, CH2, CN, a nitrile, and both undergo reduction. So basically, M is actually a reducing agent. So this is a nucleophilic substitution. This is addition elimination are also considered as nucleophilic substitution. So we have identified compound A, that is CH3, CH2, COCl. We have identified compound L, which is CH3, CH2, CN. And we have identified compound M, a reducing agent. So normally the reducing agent is lithium aluminum hydride and dry ether. Is this clear to all of you? Compound N is shown in figure 4.2. Okay. Compound N is treated with the excess of concentrated hydrochloric acid and undergoes complete hydrolysis to form three organic compounds. So see, the hydrolysis always occur at a nitriles undergo hydrolysis, amide undergoes hydrolysis, ester undergoes hydrolysis, and halogenoalkanes undergoes hydrolysis. So over here, if you see, this is the amide link. This is the amide link. So from here, the breaking occur. So see, we are getting three fragments, so three compounds are being formed. The products are isolated from the reaction mixture at pH 4. Okay. Draw the structure of the three organic products at pH 4. Assume CH3O group does not react. So see, we will get, okay. So if I draw directly over here, so on breaking, I'm just making the fragments right now. One fragment is this one. The second fragment is this one, right? And if you go for a third fragment, so third fragment is this thing only, right? Is this understandable to all of you? Okay. Just 1 minute, please. Okay. So in the acidic medium, first it gets a hydrogen, but due to the acidic medium, it actually it's a basic, so it gets one more hydrogen and become a positively charged. This gets a hydrogen, and due to the acidic medium, it gains one more hydrogen and turn into a positive charge. And over here, you will get a carboxylic acid. So same over here, you will get OH and you will get carboxylic acid. Is this clear to all of you? Because see, they have mentioned that the conditions are highly acidic, right? So if the conditions are highly acidic, so the bases which are formed are actually turned into their conjugate acids by accepting the hydrogen. Is this clear to all of you? And I think it's better to write because they have mentioned it's HCl. So actually it is going to be NH3 positive. They doesn't show NH3 positive, Cl negative. Same thing is going to happen over here, that NH3 positive and Cl negative. And over here, it's what we get carboxylic acid. One more minute, please. Yes, Fazan, it's better to write the positive and the negative ions. Okay. So compound P can be synthesized from 1-methyl 4-nitrobenzene by the route shown in figure 4.3, 1-methyl 4-nitrobenzene. Okay, is this compound in step 1? You see the NO2 is converted into NH2. So if you recall this reaction, it's a reduction. Very good, Shazil. So this reduction has a tin and concentrated hydrochloric acid as the reagent. Then in step 2, if you see the NH2, the hydrogens get displaced to get the methyl group. So it's a nucleophilic substitution, and 2 moles of CH3Cl has been used, right? So each mole display, so one of the CH3 displaces one of the hydrogen. Okay. Now in step 3, the methyl groups turn into carboxylic acid, right? So that is an oxidation. And for that oxidation, we use alkaline potassium magnate 7. And then we use hydrochloric acid or sulfuric acid to acidify it. That is oxidation. Then in step 4, if you see this carboxylic acid got an alkyl chain. So it's a condensation reaction. It's an esterification, right? Condensation. And for condensation, sulfuric acid is a catalyst. And from this, we can identify that the alcohol having this, that is the one reagent. And secondly, we need a catalyst for this reaction. Is this understandable to all of you? Okay. Now, step one is a reduction reaction. Complete the equation for this reaction. Use hydrogen to represent an atom of hydrogen from the reducing agent. Okay, so we are going to start with the atomic hydrogen. And if you see, NO2 is turning into H2. So two oxygens release which form two water. So two hydrogens over here, two hydrogens over here. Yes, very good, Shazil. So we are going to use six hydrogens and it is going to do C7, H7 and H2 plus 2 moles of water. I think it's understandable to all of you. Or instead of this, you can write C7, H9, N. Now, they are asking for the reagents and conditions. So for step one, if you recall, tin and concentrated HCl with heating. In reaction two, we have identified its nucleophilic substitution. I'm just using the shorthand. So in nucleophilic substitution, CH3, Cl, and heating is required. In reaction 3, it's oxidation. So alkaline magnate and then HCl and heat under reflux. Now, 4, if I write the molecular formula of this compound, it is going to be CH3 twice, CH, CH2, CH2OH. Okay. So CH3 twice, CH, CH2, CH2OH, and sulfuric acid and heat. Till here, is this clear to all of you? Now question number 5 and question number 6. So we have two questions left. Okay, so we'll do the, okay. Now, cumin is an aromatic hydrocarbon used in the synthesis of other useful chemicals. Complete table 5.1 to show the number of sp2 and sp3 hybridized carbon atoms that are present in the molecule of cumin. So, if you see 1, 2, 3, 4, 5, 6. So these 6 hydrogen carbons are sp2 because they all are involved in delocalization. And these 3 have no pi bond. So these 3 are sp3 hybridized, right? Now, next. Cumin can be synthesized via Friedel-Crafts alkylation reaction as shown in figure 5.2. So that is the easy reaction. Name the mechanism involved in Friedel-Crafts alkylation shown in figure 5.2. So if you recall, this is electrophilic substitution. Very good, Faizan. So it is electrophilic substitution. Now, the first step of the reaction forms this cation. Identify a suitable reagent for the formation of this cation from 2-bromopropane. So if it's a bromine, it's not necessary, but you can use anhydrous AlBr3, FeBr3, AlCl3, FeCl3. Anyone can use out of these. Okay, anyone can be written. Now, figure 5.3 shows the mechanism for the reaction of benzene with this cation. Include all relevant curly arrows and charges. So first, see, this carbon is basically positively charged. So the attack occurs from the pi system to this carbon. Now, as an intermediate, you are going to make the benzene hexagonal ring. Over here, you are going to bond this carbon with two CH3s, then the semicircle and the positive charge. And over here, you put a hydrogen over here, and then move the bond from the hydrogen to inside the circle and put the H positive at the end. Yes, it's better to write anhydrous, Shazad. So that is how you do the mechanism. Okay. The Friedel-Crafts alkylation of benzene by 1-bromopropane also produces cumene as a major product. Okay. This is the primary carbocation formed in the first step, quickly rearranges it into this cation. So that's why this is the case. Explain your answer. So see, this part is actually belongs to the AS, because in AS we have studied that the secondary and the tertiary are more stable carbocations as compared to primary one. So if this one is rearranging itself into this one, because this is the secondary carbocation, and secondary carbocation is more stable due to more alkyl groups having more uh, electron donating effect. So its positive charge is more stabilized. So if you see, this one is CH3, CH2, CH2 positive, right? And they are saying that this is going to, as soon as this form, this turn into this compound. Okay. So what happens that the proton shifts. One proton from here, one proton, one hydrogen from here shift to the terminal carbon, making the center carbon positive. So if you see, this is a primary carbocation and this one is a secondary carbocation. So they are just asking that why it rearranges into this one. So the carbocation form is primary, which rearranges to form secondary, which is more stable as positively charged carbon is bonded to more alkyl groups, causes more inductive effect. The positive charge stabilize more. I hope it's clear to all of you. Now, cumene oxidizes in air to form phenol. and propanol. Reaction 1, the enthalpy changes this. Okay. Table 5.2 gives some relevant standard entropies of reaction 1. Calculate the standard entropy change. So if you recall, the standard entropy change is equals to sum of entropies of product minus sum of entropies of reactants, right? So we have, and each one has 1 mole, so no need to multiply any entropy. So it is going to be 146 plus 200. These are the products minus 278 plus 205. So these are the reactants. Can anyone solve it and tell me the answer? Okay. Yes, very good. Thank you. So it's minus 1437. Show that reaction 1 is feasible at 25 degrees Celsius. Okay. So if the reaction is feasible, it means that the Gibbs free energy is negative. 25 means that in Kelvin it is going to be 298 Kelvin because plus 273, right? So the expression is delta G is equals to delta H minus T delta S. So delta G is equals to delta H is minus 371 minus T, which is 298 times entropy is minus 137. It's in joule. So I divided with 1000 to turn into a kilojoule. Can anyone solve it and tell me the answer? Okay, it is minus 330.174 kilojoule per mole. So delta G is negative, hence reaction is feasible. Now, the figure 5.4 shows two reactions of phenol. Okay, with bromine, it's an electrophilic substitution, and I hope you remember that with bromine, we get tribromo product. One bromine over here, one bromine over here, and one bromine over here, right? Now, state the conditions for the bromination phenol for a reaction to occur. Okay, so the second one is diazotization. Okay, so if you recall R, then R must be diazonium ion and 2 positive. So explain why these conditions are different from those for bromination of benzene. So we have already discussed this comparison of the bromination. So over here, the conditions are room temperature and aqueous, right? We use aqueous bromine, isn't it? So, and with the benzene, we use a molten bromine, pure bromine, and the air anhydrous catalyst as well. So the reason behind is that benzene is less reactive than phenol, hence benzene needs molten bromine, or better to write pure bromine, not aqueous, with catalyst. Phenol has OH group, makes it more reactive, hence no catalyst needed, and aqueous bromine is enough. Now draw the structure of compound Q. So we already done. Identify the organic reagent R. So we have identified R is a diazonium ion, or you can draw like this, or just write N2 positive. Yeah. Yes, Shazil, you are right, but it's not necessary to write all these conditions. I think that is more than enough. Yeah, you can write that it increases the electron charge density. That is enough, but no need to write up or mention the positions that 2, 4, 6. Okay, my bad. 1 minute. It is going to be over here. Sorry. Okay. Name the functional group that is formed in reaction 3. Yes, what is the functional group? Very good, Faizan. The functional group is the azo functional group. Okay, now part 5. The reaction of phenol with nitric acid produces a mixture of isomers with the molecular formula. Okay, so we have a one nitro group. Identify the two isomers that are produced in the largest quantities. So the one which is produced in the largest quantity is 2-nitrophenol, because this position is on the both sides. So we will get a higher probability of getting this. And then the second one would be 4-nitrophenol. And now they are asking the reason. So now we are going to write this reason in more detail, that OH increases electron charge density of benzene ring by delocalizing its lone pair with pi system. Electron density is increased specifically at 2, 4, and 6 positions. So the substitution are most likely to occur at these positions, and that's why the isomers which are formed are at these positions. Is this clear to all of you? I think this paper is easy. Its threshold is going to be around 65 to 70 for A. Now, question number 6. Malic anhydride is an unsaturated cyclic compound used in the formation of several polymers. Malic anhydride can be used to form malic acid and tartaric acid. Okay. So if you see, it is being hydrolyzed from here. This one get H and this one get OH. So as a result, you will get this. Now, the alkene is turning into diol. So over here, cold, dilute, acidified manganate has been used, and over here heated with sulfuric acid or hydrochloric acid. Okay. Now, malic acid reacts with ethane 1, 2 diol to form a condensation polymer. Okay. Draw a section of this polymer showing only one repeat unit. The new functional group formed should be shown fully displayed. Okay, so malic acid is, if you see, over here we have a carbons with a double bond O, and then we have OH, right? So as it's undergoing condensation with ethane diol, so it is going to release its OH. So ethane diol is two carbon containing compound and each carbon has a OH. So it releases its H and O bonds over here, then CH2, then CH2, then O, and that's it. So this is the one repeat unit. I hope it's understandable to all of you. So is this clear? Now identify a suitable reagent and conditions for reaction 2. So we have identified cold, dilute, acidified, aqueous, potassium manganate 7. And they ask you to show the displayed formula of the new functional group formed. So we have displayed it. Okay. If any one of you have any confusion, please ask. Compound U can be formed from tartaric acid in 2 steps as shown in figure 6.2. Okay. Okay. That is the step 1 and this is the reagent. And in step 2, so I think alkali has been used in step 2. So it is the type of reaction that occur in step 1. So if you look at step 1, the H is being removed, but there is a acidic condition and one more group is being added. So yeah, it can be a condensation reaction because the hydrogen from here is being removed. And if you see this compound, have a look. It is C double bond O CH3 CH3, right? So if you remove these two hydrogen and remove this oxygen, so these three combines to get a water, and this thing, when the water is formed, these two are removed. So see, these two carbons, oxygens are bonded to a carbon with the CH3 on both sides, right? So yeah, it's a condensation reaction because the water is removed. So it is a condensation reaction. Okay. You can act as a bidentate ligand. Where is you? Okay. Yeah. It can act as a bidentate ligand. What is meant by the bidentate ligand? A ligand which can form two dative bonds with transition metal ion, right? You can further add by sharing a two lone pair of electrons. Yes. Complete the three-dimensional diagram in figure 6.3. Show both stereoisomers. Okay. So U is this one, and they are saying that you are going to use this one like this one, and 3 you are there. So it means that the stereoisomerism over here is going to be optical. So what you are going to do? First make the bonds. then make the mirror images along. So the two stereoisomers are formed. Is this clear? Now, see, a student analyzes an aromatic compound X, C8H83O3 using the NMR spectroscopy. The carbon-13 NMR spectrum of X dissolved in D2O. Okay. Separate sample of X were analyzed using proton NMR spectroscopy. So if you see 1, 2, 3, 4, 5, 6, 7, 8. So all 8 carbons are different, right? All 8 carbons are chemically different. Okay. And one more thing over here, that if you see the ratio, so it indicates that there is a possibility that it contain a benzene ring because the ratio of carbon or hydrogen is almost same. If it's an alkane, so alkane has a ratio of CnH2n plus 2. So double then 2 more hydrogen. For alkene, it's CnH2n, right? So it shows that the hydrogens are relatively less, which means that it might have a benzene ring. Okay. Now, next part. Table 6.1 gives information about the analysis, and this is for proton NMR. With CdCl3, we are getting 6 protons. With D2O, we are getting 4 hyd proton signal. So it means 2 are OH because OH is displaced by D2O, right? So displaced by forming OD, so their signal disappears. So there are 2 OH groups present. Identify the number of different carbon environments present in X. So the number of different carbons present in X are 8 that we have already identified, right? Yeah, these are singlet, but these are carbon-13 NMR, Shazil in carbon-13 NMR. Uh, it's not splitting. Okay, so why I mentioned OH, so that OH can be carboxylic acid or alcohol, not NH2 because the molecule doesn't has any nitrogen in it, right? Okay. X is dissolved in D2O before obtaining its proton spectrum. To identify the OH groups present. So that's why we, okay. Now, the aromatic compound X gives a yellow precipitate when it reacts with alkaline iodine. So it means it has a CH3, C double bond O, or CH3, CH, OH. Any one group present. Okay. Use this information in C. Use the information in C to suggest the structure of. Okay. So how many OH we have? We have 2 OH, right? That's what we have identified. And there is a benzene ring. So, okay, putting a C double bond O and CH3. So it makes me 8 hydrogens, 8 carbons. Now, if I put H and O, so if I put a OH over here, and OH over here, for example. So see, this carbon, this carbon, this, and this, all the carbons having a different chemical environment. Now, count for hydrogen: 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there are 8 hydrogens, and we get 3 oxygens as well. Is this clear? Now, have a look. It's for 4 marks. I've identified this structure. If you see, we have a carbonyl, C double bond O ketone. Its signal is at 190, right? 190 to 220. So if you see, we are getting the signal in 200. So that is of a C double bond O, right? Is this understandable? Now, benzene carbons. Okay, so CH3, C neighbor to C double bond O ranges in 360, 30 to 65. So see, this is for the carbon that is bonded to carbonyl. This carbon has the signal. Okay. Now, the benzene carbons are from 110 to 160. So see, these all are the carbons in benzene. And they all are also showing different structures or different chemical environments. And if you see, they all are chemically different. So you are going to mention that C double bond from carbon 13 NMR, C double bond O at 190 to 220. CH3, C double bond O at 30 to 65. Carbons in benzene at 110 to 160. These are the major findings from the carbon 13 NMR, right? Now, two OH groups. So, in D2O, 4 signals are observed, and all hydrogens have six different chemical environments. So that's how you will answer this. So over here, we are done with the February, March 2025 paper. And now in the next class, we are going to start with October, November 2024. So we will having a class on same time tomorrow, inshallah. Any questions so far? Okay, then see you everyone tomorrow. Till then, take care. Goodbye and Allah Hafiz.